Continual advancements in biomedical imaging technology have provided insight into the inner workings of the human body like never before, facilitating diagnosis and treatment of medical maladies with ever-increasing speed and accuracy. Amongst the most prevalent imaging modalities in today's market are MRI and X-ray. MRI uses a strong magnetic field in conjunction with RF technology to orient, perturb, and reorient water molecules in soft tissue. This particular movement of molecules creates an emission of energy which can be measured to reconstruct an image corresponding to the tissue locations and features. X-ray, meanwhile, utilizes electromagnetic radiation which is readily absorbed by dense tissue and bones, but not by soft tissue. This results in a stark contrast within the region of interest and a highly accurate image reconstruction. Whilst useful in practice, both of these modalities have their shortcomings. MRI technology is very expensive to purchase and operate, and creates complications for patients with metal implants. X-ray, on the other hand, utilizes ionizing radiation which poses the risk of carcinogenically altering genetic makeup within cells. Furthermore, neither of these modalities can be performed in real time, resulting in substantial delays in diagnosis. VivoLux aims to address the shortcomings of these modalities with its Vascular Acoustic Light Imaging System, or VALIS for short. VALIS uses photoacoustic imaging, a modality which works by illuminating the ROI with light tuned to the absorption frequency of hemoglobin. Upon absorption, the vessel will emit high-frequency acoustic pulses which can be captured via ultrasound transducers and used for imaging. Using this modality, VALIS can non-invasively produce high-quality images in near real time.
Here is a view of our team members. Sean Paulson, our CEO, Glenn Ferguson, our CCO, John Kim, our CIO, Ryan Chahal, our COO, Alex McGovern, our CSO, and Stephen McLeod, our CTO. Here is a quick overview of our system. The first main component is the LEDs. The LEDs tuned to the peak absorption wavelength of hemoglobin will be mounted to the handheld transducer probe and pulsed at relatively high power. Hemoglobin within the illuminated region will absorb the photons and produce acoustic waves due to thermal expansion of the tissue. The second component is the transducer. The ultrasonic transducer will measure the acoustic waves generated from the thermal expansion of the tissues. The third component is the DAC. The signals that were obtained from the transducer will then be processed in the DAC. The last main component is the image reconstruction. The image can be reconstructed from the data processed from the DAC to reconstruct an image.
To test our hardware, we constructed a black box style enclosure. Within the enclosure, we mounted the 5 MHz single element transducer, 6 high-powered LEDs with lenses angled to center the beam, and a proximity sensor. Looking inside the enclosure, we use a prototype board to solder the LEDs, proximity sensor, and temperature sensor. You can also see the large cable going behind the prototype board which connects the transducer. To show our LEDs pulse as required, we started with a pulse frequency of 1 Hz and increased the frequency to 10 kHz. This was done just to show the LEDs are pulsed, but in practice we will use a constant frequency of 10 kHz and a duty cycle of 10%. We implemented a proximity sensor to ensure the LEDs only turn on when in close proximity to a surface. This is a safety feature to help prevent people's eyes from exposure to the extreme power of the LEDs. Last, we implemented a temperature sensor to monitor the ambient temperature inside the enclosure. This safety feature is to ensure that the housing doesn't heat up and create a potential burn hazard.
We use a boost converter to supply power to the breadboard rails at 0 and 10 volts. This acts as a positive and negative power supply to the op-amps. The Arduino provides 5 volts to act as a middle grounded point between the 0 and 10 volts provided by the boost converter. Without this DC offset, the circuit treats any voltages below 5 volts as a negative input and amplifies accordingly. For example, an input of 6 volts would be equivalent to only having plus 1 volts. If this circuit had an amplification of 2, then the output would only be 7 volts. The input of 1 volt multiplied by 2 with a DC offset of 5 added to it. Here you can see the transducer surrounded by the LEDs, whose output enters the circuit at this point. From here, the transducer output passes through 3 stages of non-inverting amplification with frequency filtering. By using potentiometers, we are able to optimize the various levels of amplifications during testing. After amplification, the signal passes through a peak detector and is displayed using either a microcontroller and monitor or an oscilloscope. Unfortunately, the op-amps we had available to use in this circuit were not optimized for high-frequency applications. The op-amps were unable to amplify signals at 5 MHz. However, we were able to produce a gain of 20 decibels at 1 MHz as seen on the oscilloscope here. Here we are demonstrating a transducer sending and receiving signals while using our amplification circuit. We are using a 40 kHz transducer since our generic op-amps are unable to pass signals produced by the 5 MHz transducer, and that is what we had on hand for testing. The pulse frequency and width are proportionate to the distance of the object the acoustic waves are reflecting off of, which we can see by moving the reflective surface closer or farther from the transducer. The reflecting surface gets closer to the transducer, the pulse frequency increases, while the pulse width decreases. We expect similar behavior from the ultrasonic pulses produced by hemoglobin.
Here's the schematic of the DAQ. There are 5 main components to this schematic: the microcontroller, the computer communications, the sampling circuitry, the safety circuitry, and the onboard user input and output. The proof of concept, we wanted to build the core of our system first to prove the design, so we only incorporated the microcontroller, communications, and sampling circuit so far. So now I'll be showing a demonstration of the DAC interfacing with the computer. So here I have a serial port open connected to the DAC, so we will take that a reset. I'll print the message. So we'll try sending a basic command, the V. It will let us know what version it is. We can set the timer speed by doing T and then a 16-bit number, so we can do 05CF, and it'll let us know it's good. If we send a malformed command, so say we only send too many characters, it'll let us know that we have bad parameter. If we try and send a command that doesn't exist, it will say it's a bad command. So now I will show you the read command. So we send R and then an ADC specific command. So in this case you want 0 to read from channel 0. Now I'll be reading. And I have a potentiometer here, and when it moves, it changes the value read. And this would be simulating the transducer. One last thing, we set the safety pin, toggle it, microcontroller freezes, and this would be the case where it shuts off the whole system.
In development of VALIS, we aim to achieve progress in terms of image reconstruction by developing this algorithm in parallel with the hardware. This required utilizing a suitably similar dataset, represented in our case by a 3D breast tissue phantom. Utilizing this phantom, the first step was to aggregate all of the vessel data into one singular slice. With the vessel data collected, the radon transform is then applied. This results in a sinogram, which is highly indicative of expected output from the parallel projection ultrasound scan about the subject region of interest. Finally, a filtered back projection is performed on the sinogram to reconstruct the original image using samples at different orientations. Note that the image reconstruction is quite accurate, though some noise persists. This will be refined in future developments. Many of our large milestones have been completed, including designing and constructing hardware components, designing software for image processing, and setting up each component to work individually. Upcoming milestones include ordering a multi-element transducer array, ordering a PCB for our LEDs and sensors, and optimizing our receiving amplifier circuit for a 5 MHz signal. Total spend thus far has been roughly $600 Canadian, and we anticipate a further expenditure of $500 in future developments for a total spend of $1,100.
In the coming weeks, we have a few improvements to implement. Firstly, we will be acquiring new op-amps that are able to operate at the high frequencies we will be using without sacrificing any performance. Secondly, we will be adding more LEDs to the enclosure in order to increase the optical power and generate a strong photoacoustic effect. Lastly, we need to implement microcontrollers and data acquisition equipment that is able to operate at high frequencies so we aren't losing or truncating any data that is produced by the LEDs and transducer. After implementing these improvements, we expect to see a signal similar to that produced by the 40 kHz transducer, but at the same frequency as our 5 MHz transducer. The different components are working separately, and we are looking forward to integrating them all into a single system with the aforementioned improvements.